So in this video, we're going to resolve an integral using the u-substitution technique when we have radical functions in the integral that we need to resolve. We're going to have two separate examples in this video. So I'm going to go ahead and rewrite the integral that I'm working with here. I have the square root of 3x plus 2 dx. I'm going to go ahead and make the u-substitution u equals 3x. I'll move it over a little bit further. U equals 3x plus 2. So we had a function composition. We had a linear function inside of a square root function. And the key here is when we take du dx, we're going to get a 3, which means du is the same as 3 dx when we multiply both sides by dx. So the derivative of u varies only by a constant from what we see out here. This is really 1 times the square root. So again, like we've been talking about, there's two ways we could handle this. So I'm going to go ahead and rewrite it in two spots, 3x plus 2 dx. So one way to handle this would be to take and say, hey, this is the integral from the square root of 3x plus 2 times, and I want a 3 dx, so I could multiply the dx by 3, but we can't arbitrarily multiply by 3 without changing the value of the integral. So we counter that by multiplying by a third, because a third of 3 is still 1. So we changed how the integral looks, but not not the value of the integral or the result that we're going to get from doing the integration. So now I'm ready to do my substitutions. I take 1/3 times the antiderivative of the square root of, and we're replacing the 3x plus 2 with u, and we're replacing the 3 dx with du. And then I want to recognize that the square root of u is really just u to the half power. And so it's a power function. I'm going to take and get 1/3 u to the, I'm going to increase the exponent by 1. So I'm going to go 1/2 plus 1 is 3/2. And I'm going to multiply by the reciprocal of that, so that when I take the derivative to check my work, it cancels. And it's going to be plus c, the constant of integration. So I get 2/6 u to the 3/2 plus c. And then we need to move it back into variable x. So we'll get, that's actually 2/9 right there. 2/9. 3 times 3 is 9, not 6. So we get 2/9. And then it's u to the 3/2 plus c. But u is just 3x plus 2. And that's good enough for our purposes. The other thing that we could have done is taken this du equals 3 dx and multiplied both sides by 1/3, which would give us 1/3 du equals dx. And we could have substituted directly in here. We could have said, hey, this is the antiderivative of the square root of 3x plus 2 is u. And dx is the same as 1/3 du. So factor that constant 1/3 out front of the integral and leave the du on the inside. But the square root of u is just u to the half power. So we're going to get 1/3 times u, increase the exponent by 1, so u to the 3/2, multiply by the reciprocal of that exponent, because 3/2 times 2/3 will equal 1. 1 times 1/3 is 1/3. So if we take the derivative, we want to get back the function that we started with, and then plus a constant of integration. So we get 1/3 times 2/3 is 2/9 u to the 3/2 plus c, and of course u is equal to 3x plus 2. So we'll do another example involving radicals. We'll do one here that's a little bit more complicated, and then we'll save an even more complicated radical example for the next video. So I'm going to go ahead and rewrite my integral. I have the integral of x times the square root of 2x plus 2 dx. And I'm going to go ahead and let u equal the 2x plus 2 that's under the radical sign. So u equals 2x plus 2. So if I take du dx. Take the derivative of both sides with respect to x, I get a 2. And this is a case that's different than the ones that we've seen so far. So this is that 1 in 19 example where when we do the u-substitution, when we take the derivative, we get a 2, which doesn't differ from what I see here by a constant. This is variable x. This has no variable x. So usually this would mean that a u-substitution isn't the right tool to use. But this is a case where a u-substitution will lead us to having the ability to make a distribution. And then after we make the distribution, we'll be able to use common techniques to find the antiderivative. So it doesn't look promising right now because this doesn't differ from this by just a constant. So I'm going to go ahead and say, hey, what would happen if I made the substitutions that I need to make? So I'm going to multiply both sides here by dx. So let's see how this plays out. Multiply both sides by a half, so I'll get a half of du equaling dx. So if we substitute, we're going to get the antiderivative. I'm going to get the antiderivative of x, and then it's going to be the square root of, and I'm replacing the 2x plus 2 with a u. And then right here, I had a mistake there, I see. So it's going to be 1/2 du equals dx because we multiply both sides of this by a half. So I can replace the dx with a half of a du. The half is a constant and will factor out front, and the du will stay inside. And so the problem that we have here, the reason why this isn't immediately useful, is now I'm integrating with respect to variable u, but I have the variable x sitting here, and I'm not going to be able to integrate that with respect to u, at least not with the tools that we currently have in our pocket. So here's the idea. The idea is we're going to come back up to our original u substitution. We had u equals 2x plus 2, and we're going to solve it for x. We're going to see what is x equal to in terms of u, or what is x as a function of u. So I would subtract 2 from both sides to get u minus 2 equals twice x, and then divide both sides by 2, which will give us that u minus 2 over 2 is x based on our original u substitution. So I can replace x with u minus 2 over 2. So I'm going to go ahead and do that on the next line. I'm going to get a half times the integral. And we're going to replace the x with u minus 2 over 2. And then we're going to rewrite the square root of u as u to the 1/2. And this is du. Right away, I want to notice that this constant 2 in the denominator could be factored out in front of the integral, which would give me 1/4, because that 2's in the denominator position. So 1/4 the integral. And what's happened here is because I wound up with a linear term here, I'm able to distribute the u to the 1/2 into the parentheses. If I'd wound up with an exponent other than 1 on the parentheses, I wouldn't be able to distribute. But because I wound up with just a 1 here, a linear term, I can distribute the u now into the parentheses. So I'm going to get, and that's what made this u substitution work, was the fact that it put me in a position to be able to distribute. So I'm going to go ahead and do u times u to the 1/2 times u is going to be u to the 2/2 plus 1/2 is u to the 3/2 minus 2 times u to the 1/2. And this is du, and now I'm in a position to integrate each of these terms. So I'm going to get 1/4 times, here I have u to the 3/2. So if you were differentiating, you would subtract 1. Because we're integrating, we're going to add 1. So I'm going to get 3/2 plus 2/2 is 5/2, and we need to multiply by the reciprocal of that. So when we take the derivative, we get 5/2 times 2/5 is 1, which is the coefficient on the base u right here, minus u to the 1/2. So I'm going to add 1 to the 1/2 to get u to the 3/2. I might as well bring my 2 down to start. And I'm going to get u to the 3/2. And I'm going to need to multiply by the reciprocal of the 3/2. So I'm going to multiply by 2/3, again, to kill the 3/2 if we were differentiating. and then it's plus a constant of integration. So a couple things that I could notice here. I noticed that a 2 shows up on each of the terms, and I could actually factor a 2 out, which would give me a 1/2. And a u to the 3/2 shows up in each of the 2 terms. So I could actually factor out a u to the 3/2, which would leave behind, I factored out a 2, so it would leave behind a 1/5. And factoring a 3/2 off of a 5/2 would leave behind a u to the 2/2, or just u, minus, I factored out a 2, which will leave behind a 2 over 3. And I factored out a u to the 3/2, so I will just have the 2/3 there, plus the constant of integration. And then if I wanted to clean up inside the parentheses a little bit, I could look at the 5 and 3 and identify that it would give me a common denominator of 15. So I could actually step out here and multiply by 15 over 15 if I wanted to clean things up a little bit. So if we do that, I'm going to take and distribute the 15 into the parentheses. And if I do that, that's going to leave behind a 1/2 times 1/15 is 1 over 30. So I'm going to have a 1 over 30 u to the 3/2 times, and then I'm going to distribute the 15 into the parentheses. So 15 times 1/5 is 3 times u is 3u, minus 15 times 2/3 is equal to 5 times 2 is 10, so I get minus 10. And now I can go ahead and convert it back into variable x world by replacing the u's with 2x plus 2. So I'm going to get 1/30th 2x plus 2 to the 3/2 times 3 times 2x plus 2 minus 10. And this term can be simplified, so I get 1 over 30 times 2x plus 2. That's an ugly x. We'll fix it. 2x plus 2 to the 3/2. It's an ugly 3/2. I guess I'll fix it. And then times, what do we get here? We get 3 times 2 is 6x's. And then we get 3 times 2 is 6 minus 10. So 3 times 2 is 6 minus 10 is minus 4. And if I wanted to, I could actually factor out a 2 from that. If I did that, I would get 2 over 30 is 1/15 times 2x plus 2 to the 3/2 times, and I factored off a 2, so I'm going to get a 3x minus 2 left behind. And that's about as simplified as I can get this particular problem. So when you're working in homework, one of the things to realize is we could have substituted back in for u at any point here. And one of the issues you're going to run into when you have an answer key is, asking that question, when did they stop simplifying? And if I stop simplifying earlier than the person who made the answer key did, or if I stop simplifying later than did the person who made the answer key, my answer may look the same, my answer may look different but be equivalent. So just because my answer doesn't look the same doesn't mean that I'm wrong, but it does mean I might need to think about whether the answer I have is equivalent to the one that I'm seeing in the answer key.